resampling. Why is a resampling done? Resampling is done in statistics to obtain additional information about a population or to less the variability and reliability of statistical estimates. It involves creating new samples or data sets by drawing observations from an existing data set through random sampling techniques. The two main methods of resampling are bootstrapping and permutation. The primary reasons for performing resamplings are: number 1, estimating sampling variability. Resampling allows us to estimate the sampling distribution of statistics without relying on theoretical assumptions. By repeatedly sampling from the available data, we can create multiple simulated data sets and calculate the desired statistics for each data set. This provides an estimate of variability or uncertainty associated with the statistics, such as standard error or confidence interval. Number 2, hypothesis testing and significance testing. Resampling techniques such as permutation test can be used for hypothesis testing when the assumptions of traditional parametric tests are violated. Permutation tests involve randomly permuting the observed data to create a null distribution under the null hypothesis. By comparing the observed static to the null distribution, we can assess the statistical significance of the result. Assessment and validation. Resampling is often employed in model assessment and validation. Validation to evaluate the performance of predictive models. Techniques like cross-validation, bootstrapping can provide estimates of models' predictive accuracy, assess its generalization ability, and help in model selection. So this is model assessment validation. Number 4, handling small sample sizes. Resampling methods can be particularly useful when dealing with small sample sizes. By generating multiple resampling from available data, it is possible to obtain more stable estimates and gain insights into the behavior and statistical procedures. Overall, the resampling techniques are valuable tools in statistical analysis as they provide a way to explore and understand the properties of data, assess uncertainty, and make more robust inferences and conclusions. Question number 17. What are the difference between oversampling, overfitting? What are the difference between overfitting and underfitting? In statistics and machine learning, one of the most common tasks is to fit a model to a set of training data so as to be able to make reliable predictions on general untrained data. In overfitting, a statistical model describes random error or noise instead of underlying relationship. Overfitting occurs when a model is excessively complex, such as having too many parameters relative to the number of observations. A model that has been overfitted has poor predictive performance and it overreacts to minor fluctuations in the training data. Underfitting occurs when the statistical model machine learning algorithm cannot capture the underlying trend of the data. Underfitting would occur, for example, when fitting a linear model to non-linear data. Such a model too would have poor predictive performance. Overfitting and underfitting are two common problems encountered in the machine learning model. The difference between overfitting and underfitting. Overfitting occurs when a model performs well on the training data but fails to generalize well on unseen or new data. It happens when the model learns the training data too well, includes noise or random fluctuation, and captures the idiosyncrasies of the training set. Overfitting often results in a complex and overly flexible model that is too specific to training data. The model may exhibit low bias but high variance. Signs of overfitting include significant differences in performance between the training and validation test datasets, and the model may have excessive complexity or too excessive complexity of too many parameters. To mitigate overfitting, techniques such as regularization, feature selection, and cross-validation can be employed. These methods aim to simplify the model and reduce its complexity. Underfitting. Underfitting occurs when a model is too simple or lacks the capacity to capture the underlying patterns in the data. It happens when the model is not able to learn the important relationship between the features and the target variables. Underfitting often results in high bias model that oversimplifies the data. The model may have difficulty capturing the complexity and nuances of underlying problems. Signs of underfitting include poor performance on both the training and validation test datasets, and the model may exhibit high error rates or low accuracy. To address underfitting, one can consider increasing the complexity of model by adding more features, using a more flexible algorithm, or reducing the regularization. In summary, the overfitting occurs when a model is too complex and learns the training data too well, while underfitting occurs when a model is too simple and fails to capture the underlying pattern in the data. Balancing between these two extremes is crucial for building models that generalize well to new data. Question number 10. How to combat overfitting and underfitting? Overfitting and underfitting in machine learning models. Several techniques can be employed. Here are some to address these issues. Combating overfitting. First, regularization. Regularization techniques such as L1 and L2 regularization add a penalty term to loss function to discourage overly complex models. This helps prevent overfitting by reducing the magnitude of the model's parameters. Number 2. Cross-validation. Cross-validation helps assess the model's performance on unseen data. Techniques like k-fold cross-validation can provide more reliable estimates of the model's generalization performance. Number 3. Feature selection. Removing irrelevant or redundant feature can reduce model complexity and prevent overfitting. Feature selection methods like forward selection, backward elimination, or regularization-based selection can be employed. Early stopping. Monitoring the model's performance on a validation set during training and stopping the training process when the validation error starts to increase can prevent overfitting. Dropout. Dropout is the regularization technique commonly used in neural network. It randomly drops out a portion of neurons during training, forcing the network to learn redundant representations and reducing over-reliance on specific features. Ensemble methods. Combining multiple models such as using techniques like bagging, bootstrap aggregating, or boosting can help reduce overfitting by averaging what individual model biases and variances. Combating underfitting. Feature engineering. Generating more relevant features or transforming existing feature can help capture the underlying pattern in the data and improve the model's performance. Model complexity. Increasing the complexity of model by adding more layers or nodes in neural network, increasing the degree of polynomial regression, or using more flexible algorithm can help address underfitting. Collecting more data. Gathering additional data can provide the model with more diverse and representative examples, allowing it to learn better and reduce underfitting. Adjusting hyperparameters. Tuning hyperparameters such as learning rate, regularization, parameter, or model architecture can help find the right balance between underfitting and overfitting. Model selection. Trying different algorithm or model families can help identify models that better capture the underlying patterns in the data. Ensemble methods. Combining multiple models through techniques like bagging or boosting can help improve performance by leveraging the strength of different models. It's important to note that specific techniques to combat overfitting or underfitting may vary depending on problem, the data set, and chosen modeling approach. It's recommended to experiment and iterate to find the most effective strategies for a given scenario. What is regularization? Why is it useful? Regularization is a technique used in machine learning and statistical modeling to prevent Regularization is a technique used in machine learning and statistical model to prevent overfitting and improve the generalization performance of a model. It involves adding a penalty term to the loss function during the training process. The penalty term discourages the model from assigning excessive importance to certain features or becoming too complex. Regularization is useful for several reasons. Number 1. Overfitting prevention. Regularization helps prevent overfitting, which occurs when a model performs well on training data but fails to generalize to new unseen data. By adding a penalty term, the regularization reduces the model's tendency to fit the noise or idiosyncrasies present in the training data, leading to better generalization. Bias variance trade-off. Regularization helps strike a balance between bias and variance in the model. A model with low complexity, high bias may unfit the data, while a model with high complexity, high variance may overfit the data. Regularization allows us to control model's complexity by adding the regularization parameter, providing a trade-off between bias and variance. Feature selection. Regularization techniques such as 11 regularization, lasso, and drive feature weights to 0 effectively performing feature selection. This is particularly useful when dealing with a dataset with a large number of features, as it helps identify most important predictors and discard irrelevant ones. 4. Improved model interpretability. Regularization can promote sparsity in the model, resulting in a smaller set of influential features. This can make the model more interpretable by focusing on most relevant variables and eliminating noise or irrelevant factors. Number 5. Robustness to outliers. Regularization can make the model more robust to outliers or noisy data points. By discouraging large coefficients, it reduces the impact of individual observations that may have disproportionately large influence on the model's prediction. Overall, the regularization helps to control model complexity, improve generalization, enhance interpretability, and handle noisy or high-dimensional dataset. It is a powerful tool in machine learning that aids in building more reliable and effective models. What is the law of large numbers? The law of large numbers is a fundamental concept in probability theory and statistics. It states that as the number of independent and identically distributed random variables increases, their sample means or average converges to the expected value or population mean. In simple terms, the law of large numbers suggests that if we repeatedly perform an experiment or draw samples from a population, the average of those samples will become increasingly close to the true population average as we collect more data. The weak law of large numbers and the law of large numbers. Weak law of large numbers. This version states that the sample size increases the sample mean conversion in probability to population mean. It means that the probability that the sample mean deviates from population mean by a certain amount becomes arbitrarily small as the sample size grows. Second, strong law of large numbers. This version states that sample mean converges almost surely to the population. It means that with probability 1, the sample mean will eventually become arbitrarily close to population mean as the sample size increases. In practical terms, the law of large numbers has important implications for statistics and data analysis. It provides a theoretical foundation for making inferences about population parameters based on sample data. It suggests that by collecting a sufficiently large sample, we can estimate population parameter with a high degree of accuracy. The law of large numbers is also crucial in development of many statistical techniques such as hypothesis testing, confidence interval, and regression analysis. What are confounding variables? The confounding variables, also known as confounders, are extraneous variables that are related to both the independent variables and dependent variables in a state. They can introduce a spurious association or distortion in the observed relationship between the variables of interest. Confounding variables can lead to incorrect conclusions or interpretations about the two causal relationship between independent and dependent variables. In research studies, the goal is to establish a cause and effect relationship between independent variables and dependent variables. However, confounding variables can interfere with this process by introducing alternative explanations for the observed relationship. Further understand confounding variables, consider an example. Let's say a researcher wants to investigate the effect of a new drug on blood pressure. The independent variable is the administration of drug and the dependent variable is the blood pressure measurement. However, the researcher may unintentionally overlook the fact that age also associated with both the drug administration and the blood pressure. Age in this case is a confounding variable because it influences both independent and dependent variables. If the researcher failed to account for age in analysis, any observed effect of the drug on the blood pressure may be confounded by influence and up to address confounding variables. Researchers employ various strategies including study design, statistical technique, and controlling for potential confounder. Randomization, stratification, matching, and regression analysis are common approaches to mitigate the impact of confounding variables and obtain more accurate estimates of the true relationship between independent and dependent variables. In summary, confounding variables are variables that can distort the relationship between the independent and dependent variable in a study. It is essential to identify and address confounding variables to ensure valid and reliable research findings. Confounder variables that influences both dependent and independent variable. If you are researching whether a lack of exercise leads to weight gain, lack of exercise is equal to independent variable, weight gain is equal to dependent variable. A confounding variable here would be any other variable that affects both of these variables such as age of subject.